Good. So good morning. My name is Athanasios. I'm a professor at the University of Piraeus, Greece, and I am the head of the Telecommunication Systems Laboratory. My view is a wireless communication engineer view with a little knowledge on the science of astronomy. And I will present you some RFI measurement results from the campaign that was conducted last July in 3 sites in Crete. Okay, so the contents of the presentation are shown in this slide. Initially, I will present you some details on the RFI protocol that was used for the measurements, the measurement equipment, some characteristics of the measurement equipment that we have used, the calibration procedure that we followed, and then I will present you the main results from the 3 sites, Skinakas Observatory, the Nida Plateau, and some measurements from the campus of Forth. And I will conclude my presentation with some major points that we have to keep in mind. So, first of all, I would like to start with ITU, with International Telecommunication Union, saying that radio astronomy is a regulated service. And according to the radio regulations, is the astronomy based on the reception of radio waves of cosmic origin. Actually, in the radio regulations, there are 2 articles, Article 4 and Article 29. Especially, Article 29 is dedicated to radio astronomy service and provides measures and protection guidelines for the stations of this service. Now, in 1960, the vulnerability of radio astronomy to interference was documented by the CCIR, and then in 2003, we have some refined and improved document that was published in the recommendation ITU-R 769, which is very important for radio astronomy service. 2 years later, the Committee for Radio Astronomy Frequencies released the 3rd edition of the Handbook for Radio Astronomy. It's a handbook that provides a comprehensive review of matters related to spectrum management and the protection of the science of radio astronomy against harmful interference. Now, a very important contribution of the recommendation of ITU, the 769, is some tables with the threshold levels of interference, which are detrimental to radio astronomy. Here you can see these values in dB watt per square meter per hertz, and also in Janskis. These are two different units that we use for the same thing. The region of interest, the frequency region of interest, is from 1 giga to 3 giga for Argos telescope. Okay, so first of all, to detect the RFI down to the levels deemed harmful in ITU recommendation for both polarizations would require really many months of continuous observations and measurements. So the square kilometer array started a continuous work on this issue, on a new RFI protocol, which was published in Memo 37. This memo defines a protocol for RFI measurements, which can be performed within few weeks. So the protocol that was set by the Memo 37 seeks to identify all these signals, or the interference signals originating from terrestrial or airborne sources, but not from satellites or other astrophysical sources. And also, this protocol seems to be sufficient for the selection of sites for the radio telescope installation. Now, in this memo, we have 2 modes of signals and measurements. We have mode 1 measurements to detect strong RFIs, which potentially threatens the linearity of the receivers, and this is really important. And the second measurements, the mode 2 measurements, is for weak RFI signals, which threatens to obscure weak signals of interest. So for these 2 different modes of measurements, we have different sensitivity requirements, and these are proposed through choice of what we call dual time and resolution bandwidth for each frequency band that was defined in the protocol. Now, the frequency bands relative to Argos telescope are from 960 megahertz to 1400 megahertz, and also from 14 to 100 megahertz to 3 giga. As you can see, we have different resolution bandwidths. For the first band, we have 1 mega resolution bandwidth. For the second band, we have 30 kilohertz, really smaller. And we have completely different dual time. The dual time for the first band is 2 nanoseconds, whereas for the second band is just 10 milliseconds. The big difference here is the number of repetitions, the number of samples that we have to record during the measurements. For the first band, we have 1 million samples that we have to measure, and for the second band, just one sample. Now, the value, the SOH value, is the expected flux density at 0 elevation of the horizon for signals matched in bandwidth, so either in 1 mega or in 30 kilohertz, that generates minus 100 dBm at the antenna terminals. Now, the dual time that was mentioned earlier is the length of time that a channel, which is equal to the resolution bandwidth, is examined. So it's actually the integration time within the resolution bandwidth of our receiver. Now, the protocol that we have followed in our measurements closely follows the protocol of square kilometer array, the MEMO 37. We conducted only mode 1 measurements. So we were looking for the strong RFI signals. The measurement frequency range was from 900 megahertz to approximately 3 giga. The antenna height was set to 5 meters. We have measured both polarizations, vertical and horizontal. We covered all the azimuth range, the 360 degrees, using a directional antenna. Also, you will see the antenna pattern of this antenna that we have used, and you will understand that we need just 5 azimuthal orientations, directions to measure in order to cover the whole cycle. Also, we have used 1 more, so 5 azimuthal and 1 orientation towards sky in order to measure also signals from satellites. These are the settings that we have used for the spectrum analyzer and for the 2 different bands, band 1 and band 2. The main difference is, again, the resolution bandwidth, but also the dual time. And also we have used power RMS averaging. We will see some more details later on. The most restrictive thing in the protocol, in the SKA protocol, is the 1 million samples that we have to record during mode 1 measurements. So this means that we would need approximately 3 hours per polarization per azimuthal orientation. This is really difficult. So we had to design something different here. So we decided to go for this solution, which is depicted in this figure. Actually, we have 500 megahertz span in the spectrum analyzer. There are 4,000 frequency beams. So each frequency beam, it's 125 kilohertz wide. So we have 8 samples within each 1 megahertz, within each resolution bandwidth, say. With a sweep time of 8 milliseconds that we have used, the time spent in each frequency beam is now 2 microseconds. So we have a tunable digital IF filter that is swept 8 times within 1 megahertz. So we have 8 independent time and slightly frequency shifted samples that are assigned to the same nominal frequency, as you can see in the figure. For example, here for 901 megahertz, we have 8 samples that are shifted by 125 kilohertz, and the time spent within each frequency beam is just 2 microseconds. So this setting allows us for a reduced number of repetitions. Instead of 1 million, we had 125,000 samples. repetitions. Sorry, repetitions. Now, the measurement equipment we have used. This is the chain that we selected to use. Actually, it was not our first choice. We wanted to put the LNA in front of the chain after the antenna, but this was not possible due to the very strong signals that we measured in the area. And when we used the LNA in front of the chain, we had really big problems with the linearity operation, the linear operation of the low noise amplifier. So we had to move the low noise amplifier at the end of the chain in order to have the attenuation set by the cable, which was approximately 4 to 5 dB in the frequency range that we measured. And also, depending on the site, as you can see also in the table in the slide, we used or not an attenuator. So for Skinagas and for Nida Plateau, we didn't use any attenuator. So this block here was missing, but at the fourth campus, we used an extra attenuation of 5 dB. Then we had the bandpass filter, and then we had the LNA and the spectrum analyzer, as I told you. And the whole operation was controlled by the laptop. Now, the two chains that we have used, we have chain B. We call chain B because chain A was with LNA in front of the chain, but we never used this chain. So we have chain B with 0 dB attenuator and chain B with 5 dB attenuator. You can see also that we have calculated two different noise temperature of the chain. The first, when we had no attenuation, internal attenuation at the spectrum analyzer, and when we had 10 dB attenuator internal at the spectrum analyzer. So we used the 10 dB almost in all measurement sites, and the final values, calculated values for the noise temperature of the chains was 2,800 Ks for chain B with no attenuator and 9.5 K for the second chain, which is well below the threshold that was set by the protocol, the SKA protocol, which was 30,000 K. Now, this is the pattern. These are the patterns of the antenna, the horizontal and vertical patterns of the antenna. You can see that we have. We were looking for the 6 dB beam width of these patterns, and these 6 dB beam widths are approximately 75 degrees. So we can use 5 different azimuthal directions to cover the whole cycle during our measurements. These are the S parameters versus frequency for chain B without attenuator. So it's the first option of the chain. You can see with the red color the S21 parameter, which is the gain of our chain. And you can see that it's well above 30 dBs as a gain of the chain. And also with the blue color is the curve S11, which is actually the reflection coefficient, something analog to the reflection coefficient of our chain, which is well below the minus 10 dBs, which is quite good. And the corresponding values for the second chain with 5 dB attenuator are shown in these two figures. It is below 30 dB now, the gain of our chain. And also you can see the S11 parameter. Good. Now, prior to any measurement and after any measurement, we conducted a calibration. We had a calibration procedure. So we removed the antenna and we connected a noise source, a key site noise source, with an effective noise ratio of 6 dB. And we measured the gain of the chain and also the noise temperature of our chain. So the noise figure measurements of the device under test, which is the whole chain in our case, are carried out using the Y-factor method that is a well-known method for calibration and for measuring the noise figure. Good, and these are typical results from the calibration procedure. At the left, we have the typical receiver gain. We have two different colors for the two different bands. So the first band is up to 1400 megahertz and then up to 3 giga. And you can see the receiver gain and also the noise temperature of our receiving system, which is quite good with respect to the 30,000 K that was set as a threshold from the SKA protocol. Now, the results that I will present you are based on this basic equation. So at the denominator, we have the measured power from the spectral analyzer, which is a function, of course, of frequency. We have the squared wavelength at the denominator. We have the resolution bandwidth that we have used, which is different for the two bands. The antenna gain, again, as a function of frequency, and also the receiver chain gain, which was calculated from the calibration prior to our measurements. And the result of this equation, of course, is the power spectral flux density, which is measured in watts per square meter per hertz. Now, the results for the first site. As you can see, the Skinnacas Observatory, for those who have not ever been in this place, is almost on the center of Crete. It's at an elevation of 1,740 meters. You can see in these pictures where we have put the measuring equipment. These are the 5 different azimuthal directions, so 5 + 1 toward the sky. And we selected the first one in 48 degrees since it was the direction where we have seen that we received the strongest signals from Heraklion city. And then we moved 72 degrees around the clock. So for all the results that follow, we have put all the measurements, all the samples that we have recorded in buckets. So we had one bucket for each frequency. So we have millions of samples for each frequency. So we were able to calculate the probability density function of the power flux spectral density for each frequency. And also we could calculate the cumulative distribution function of the power flux density for different frequencies. We can select whichever frequency we want, and we can calculate the cumulative distribution function. These are just indicative results, just to explain you how we calculated the percentiles that you will see in the following figure. So this is the main result for Skinnacas Observatory and for the first band from 900 megahertz to 1400 megahertz. What we see here is 5 different values, is the 10th percentile, 15th, 80th, the max, and the mean value, with different colors in this figure. The important thing here is that we have many infrequent signals, which are depicted here with the red color, because this is the maximum value, which is not a steady signal, but there are some infrequent signals with strong, very strong signals. And also you can see that the 10th percentile is really low, is below minus 180 dBW per square meter per hertz. On the left of the figure, you can see the mobile communications band, which is below 960 megahertz. And then on the right of 1 giga is the place where we would like to operate our telescope. This is not a very good picture. And the reason is that Skinnacas is at 1,750 meters, and we have line of sight with every transmitting equipment around the Psiloritis. So you can see transmitters from the northern part of Crete, and also from the southern part of Crete. This is the situation from the second band, from 1400 megahertz to 3 giga. I have also identified here some frequencies from known sources. So we have signals from mobile communication systems, and mobile communication systems use really many frequency bands here. But also we have identified the ISM band, which is mainly, we believe, from satellite signals. Since there was no Wi-Fi in this place, where there was no Bluetooth in this place, all we have switched off our phones, so there was no known source around the place. And on the right part of the figure, you can see also some peaks that are from radars, aviation and maritime radars in Crete. These are typical. Yes, please.
Well, you said that you had close to mobiles. If someone has his mobile open, how far you could detect it? I mean,
We could not detect it, but it's not close to our equipment. I mean, close to our equipment, at least 500 meters. I think there was no transmission.
So if it was after 500 meters, you will not get detected.
We could not.
You could not.
No. But it's up to Skinnacas. I mean, it's really, there was not many people up there, 2 or 3. Sometimes we were alone. I mean, we were just 3 or 4 of us. It's no one else.
Maybe someone in general is away from you, but you cannot see. It's a shepherd with his 4x4.
Yeah.
I think how far would it be that you cannot detect it?
I don't know. I cannot answer this question. Okay.
I remember the Wi-Fi.
No, George, not Papadakis. What was the other name? George Paterakis. Sorry, George. We had switched off it. Yes. Yeah.
Wi-Fi was closed, but I think someone else.
I suggest you continue the
Okay. Okay. So these also are the same result, but different percentiles. You can see here the 10% and the 90th percentile for the same band for Skinnacas. And these are some indicative waterfalls showing just a few time samples. Here you can see only 40,000 samples, time samples for 200 megahertz from 1 giga to 1.2 giga. And you can see that there are some steady, some persistent signals, which one is in 1030 and one in 1090, which is clearly radar, which is clearly the secondary surveillance radar from the airport. And also, you can see here, it's the second part of this band is from 1200 megahertz up to 1400 megahertz. Again, we have some persistent signals, which again are from radars. This is for sure, and also some infrequent signals that you can identify within this waterfall figure. Now, the second side was Nida Plateau. Nida Plateau, which is at 1,350 meters. It is approximately 400 meters lower than the Skinnacas observatory. You can see the Skinnacas observatory here. This is here, and the Nida Plateau is here. It's a very, very nice place. There is a physical shielding with mountains around the place. So this is the east-west direction, as you can see in this picture. And also, this is the north-south direction. So you can see that there are mountains all around the place. And this is the reason that we had really lower signals measured in this site. We have used the same azimuthal orientations for our measurements as in Skinnakas Observatory. And this is the corresponding result for the first band. You can see that especially the 10th, 15th, and 90th percentiles are really low, but also the mean value is also low compared to the Skinnakas Observatory. So this is really low. But again, there are some infrequent signals which give some peaks to our measurements. And the corresponding figure for the second band is this one. We have really less bands used by mobile operators in this place. We have just 2 bands here instead of 4 that we had in Skinnakas. And also, again, we have the ISM band where, for sure, again, there was no Wi-Fi or Bluetooth around the place. And also, again, you can see at the right hand of the figure some peaks that come from radars, from aviation maritime radars. And this is the corresponding results for the 10th and 19th percentile for the same band for Nida Plateau. You can identify here some very nice frequency bands that we can measure whatever you want as astronomers. Okay, and these are, again, some indicative PDF, probability density functions, and cumulative distribution functions for each frequency that you want to depict. Good, and the corresponding waterfalls, the values are really low here, as you can see, in the first 200 megahertz of the first band. And this is the second part of the same band from 1.2 to 1.4 giga, where we have really infrequent signals. The number of samples that we have depicted here is just 20,000 samples from one orientation, one polarization. It was really difficult, really impossible to depict all the samples in one waterfall. It's really impossible. If you have millions of data, you cannot produce such a waterfall for all this data. Good. Moving to the third site, it's the fourth campus with an elevation of 50 meters above sea level. We measured 3 different directions here. The place that we have measured is 100 or 200 meters from this place that we are now. Also, this place has a physical shield. There is a hill. You can see there are approximately 20 to 25 meters high hill. So this is really good, since we could reduce we could measure lower signals, especially from some base stations of mobile operators. This is the situation for band 1 from 900 megahertz to 1400 megahertz. Again, all the percentiles take low values, which is quite important. We do have, again, peaks with infrequent signals. This is the situation for the second band. We have the mobile communication bands and also some ISM band, but as you can see, the radars, the signal from the radars are really low. And the reason is that the airport is towards the direction where the hill was. So we were a bit covered by the hill, and this is good. And also, this is the situation for the 10th and the 90th percentile for the same place, the same band. indicative probability density functions, and also indicative waterfalls with infrequent signals, as you can see, and with really low, very low signals in this second part of the first band from 1200 to 1400 megahertz. So, concluding this presentation, all the results that are contained in the corresponding report and presented today should not be interpreted as a comprehensive evaluation of the RFI site, for sure. Among the three sites, the NIDA plateau is the one with the lowest RFI signal levels. It is the most suitable among the three for the placement of the Argos radio telescope. Skinnacas preserves line of sight with many RF transmitters in the wider area of Crete, resulting in increased signal strength despite the large distance from the transmitting the emitting equipment. Fourth campus may be considered for the installation of the Argos Pathfinder, provided that the placement of the Pathfinder is close to the one where the measurements took place. This is important since we have the hill, as I told you. Apart from the expected signals coming from known operators, mobile communication operators, other signals, many other signals were measured, a plethora of other signals were measured. Many of these come from aviation and maritime radars. The band 1 was heavily populated in all sites, this is for sure, whereas in band 2, I think that we can have large consecutive frequency intervals with reduced interference. And finally, we had a great time in Crete last July, and thank you very much for your attention.
Thank you very much. So let's move to we have some time for some questions. So I think let me see if anyone online has any questions. Okay.
Sorry, I was muted. So does anyone online have any question? Should work now. So just to put a few things into context, I think from what we've seen now, so originally we were considering Skinnacas for the Pathfinder because it's in the middle of nowhere. It's a mountain, but it's only shape around, so we will see today. But it turns out that that was not the case. We can see a lot of the military data there. So, unsurprisingly, the best site for that turns out to be here. That has some additional advantages. For instance, we don't have to spec out the dishes for 200-kilometer wind gusts, which reduces the cost a lot. We have access to displays 24/7, which is not the case for Skinnacas, and we also have high-speed fiber and everything, all the comforts of being in the campus of the large research center. So we made the decision, and the board of directors also is supporting that, and so the Pathfinder will be actually placed here. So next time we have this meeting, probably we'll also have a Pathfinder to play around and see.
John, so the same question as I asked yesterday about notch filters. I mean, the maximum signal strength on the fourth campus site is a good 20 dB higher than any of the other sites, albeit granted with less occupancy in the band. Has anyone looked at, specifically for these ambient temperature LNAs, what the responses are and whether or not that's going to require notches in the band?
Yuan, is that you?
Yeah.
Okay, so yes, we would need some notch filters in order to filter out all the well-known mobile communication operators signals. That's for sure. And I'm talking about mobile communication operator signals since these are very well placed in the band, and we know exactly, and they follow the requirements set by the authorities in Greece. So this is really feasible, and we should do that, not filters for the mobile operators. Then we have some very specific frequencies from the radars. For example, 1 giga 30 mega, I think, 1 giga 90 megahertz, and some frequencies from the primary surveillance radar. So there are some very well-known frequencies that we can filter out, if that's the question.
Yeah, I'm just wondering how much of the bands, because I mean, those notch filters are going to be wider than the signals that they're notching. I'm just wondering how much of the band is going to be extra lost due to notches being introduced, and also what that's going to do to the overall system temperature.
This is a difficult question.
No, I appreciate that. Yeah.
I'm not sure.
This is something we're going to learn, I guess. It's part of commission.
I think we should go to specific bands and see what we can achieve there. I mean, we have to focus to specific frequency ranges and see what we can achieve.
The question actually, if this finished.
Yeah, you can speak.
If I recall correctly from the front end overview yesterday, that there was no filter before the other day. So did you also perform measurements out of this band?
No, there is a filter. There is a band pass filter.
No, but for the front end of the Argos system.
Yesterday, it was presented how we think that we will build the
front end.
The front end.
This is different. I mean,
but the low noise amplifier will see all the signals below 900 megahertz as well. So I'm asking if you also perform these measurements below 900 megahertz to get an indication of what the.
We're not going to measure below 1 giga. Actually, we need some very good filters to filter out all the signals below 1 giga. So also in the front end. But this is what Christoph and Gudolf will.
So you'll filter before the low noise amplifier. That's the intention.
Yeah, for sure, yeah. For sure. Otherwise, we will have a non-linear operation of the amplifiers.
Yeah,
for sure.
So yeah, it's a pity that the first speaker couldn't make it, because I would like to see how this compared to other sites in Europe, but probably I don't know. Is there any what does that look like for the last one? So compared to Ephesus, I don't know if the speakers what to talk about.
Sorry, say that again.
So I was just wondering how from my experience, I think Lida is as good as it gets for a European site. Because it's very close to big cities. But for me, it would be nice to see some comparison with other big observatories like Ephesus or Astron or Jodelberg.
Okay. Well, I don't have numbers for RFI Jodelberg on top of my head, so I cannot tell you how it compares. But it is something that we can retrieve some values. Yes. Yeah.
Yeah. So I also observed with Jodelberg.
The good thing with this measurement is that we followed the SKA protocol. So we can compare this data
with the data measured in other places following the same protocol. So this would be really nice to see what's going on in different places in Europe.
Yeah, well, I can get in touch with our 5 people, show you the cost statistics and see whether we can compare. I had actually a question. Once your site is confirmed, say it is NIDA plateau for the instrument, do you have any plan or do you think is necessary to try and reach an agreement for a radio quiet zone, try to, just to protect the site from any changes?
Yeah, there are authorities in Greece that we can contact too, and we will do that.
Okay.
Actually, the authorities have
the decision.
So we already
Yes.
have some connection with them. But that's too far in the future.
No, of course it is.
We will ask for the protection. We can apply for the protection, and we can get the protection.
There is some legal framework.
Yeah. Okay. That's good. And then second thing, I guess, given the frequency, maybe you're not worried about the satellite constellations, giving us a bit of a nightmare. To be honest, the new Starlink and so on and so forth. So I guess maybe this frequency maybe is not too much of a problem.
Up to now, I think that the main issue is within the ISM band, which is the, let me show you again, the ISM band. And you see that band,
Yes.
where this is the S band, we call it, and the satellite communication use mostly this band for transmitting. So this is well set, as you can see, so we can use again a notch filter in this place.
I know there were some recent results about all these Starlink satellites leaking, but that was I think much lower frequency.
The thing
Who knows?
so their downlink frequency is high, it's 15 gigahertz or something. That's the worst, and it's no problem for you. But depending on which equipment they have on board, there is some unintentional RFI, right? And so it could pop up here and there, and they could change technology. So with the SKA and other interested partners, we are in a conversation with them because some of them is vital to their operation, and some of them is not, right? So they can, there are some engineering modifications that they can make if they are amenable to, because of course this is completely unregulated. Right, and they are not breaking any regulation. So the only thing that we can do is to ask nicely. So far, they have been cooperative to say, maybe I don't know if you shield it differently. And the good thing is that it seems like they evolve very quickly, the various generations of their equipment. So hopefully, but you never know.
Yes, and that will be a problem for everybody. Yeah, as long as they fly on the skies.
This is probably, as I say, it's probably not too much for you guys, but I was a bit astonished that after all the working, protecting our radio band, the radio quiet zone, something like that blows everything out of the water. So.
Yeah, it's also a huge problem for optical. It's the reflection of the Starlink satellites.
Also for optical. So.
Okay. Actually, because of those incidents, there are now projects and proposals for projects for monitoring the sky for communications that may introduce RFI to radio telescopes or other land communications. So one thought that I had is that we could, if
the performance of the servers that we have allows us to have a monitoring for telecommunication signals. So as we capture the signals to detect any of the events that we would like in deep space, simultaneously we could check the band for telecommunication signals in order to detect soon enough that there is a new communication in a part of the band that it shouldn't be, and either try and go and say, okay, some of you transmit in a band that you shouldn't, or with some other mean try to mitigate that. This is we are doing some work on detecting telecommunication signals in low Earth orbit satellites. So we could put our code also in the array and detect telecom signals directly on the array and somehow spot the part of the band that is being used for telecoms. I don't know, filter out.
So the idea is to detect. So the next step may be the mitigation.
Mitigation, yes.
Something like, I don't know
if it is possible.
Like noise cancellation, something like that. So
yeah.
So I think one exercise that would be interesting to do with the data that we already have is to correlate with non-satellite orbits to see if there's a correlation. So that's something that we could probably use. Okay, is there any other questions from the people online? Oh, okay, so there seems to be some problem with the microphone that we are using. Okay, so I will mute the microphone anyways now for the next speaker, and then we can try to work this out. Oh, Yuan, do you have a question?
Just one quick practical question, John. Is computing rack space already sorted in Forth for taking the equipment that required for the Pathfinder?
I would say yes. I see Stefanos is
yeah, I have checked it.
Excellent.
Okay.